So, next we will start with a new topic which is known as boundary scan, and it is also used in core based testing. So, boundary scan means, as the name suggests, through the boundary we will have some sort of scan lines. Okay. So, this was very much popular when we have these PCB based designs, where these individual chips, like in the PCB, if this is the PCB, we have got these chips were there. So, this is a one chip. So, this is another chip, this is another chip. So, what happens is that while so there are connections between the chips. So, there may be signal lines running like this, there may be signal lines running like this. Now, this board, it has got some inputs. Okay. So, these are the board level inputs and these are the board level outputs. Now, you see that to test a particular chip. So, if I want to test this particular chip whether it is working or not. So, at the time of manufacturing, so these chips were tested. So, that is fine, and at the time of manufacturing the board. So, what we could do, we assume that these chips are all right, but these interconnections we needed to test. So, that was done, but later on when the board is operating, so if there is some problem that has grown, so we need to check whether these chips are okay or not. So, for that purpose, so without picking the chip out of the slot, so if we want to test it, then we have to apply some test pattern to this chip, for example. Now, since this signal line is coming from here, so I need to make this chip operate in such a fashion, so that the desired output comes at this point, and that is basically a very cumbersome process, because chips are not that simple as logic gates, individual logic gates. So, at a circuit level we could try to do a justification and try to get that using some ATPG algorithm. So, we could try to justify how this line can be made to 0 or 1, but at a board level that is not possible. So, what is done is that every chip that we have, so around that we have got a chain of flip flops. Okay. So, we have got some sort of chain of flip flops and they are connected in a chain like this. Similarly, this chip is also having some chain of flip flops around it, and this chain is connected to this, and ultimately it is connected from a system input, and here it may be this is the last few flip flops and they are connected to the output. So, what is happening is that we can pass any pattern into this chain, and we can say after how many shifts the pattern will reach the particular chip input, and that way these inputs can be fed to this chip. So, maybe I have got connections like this, and these inputs can be fed to the chip, and similarly the responses from the chip can also be collected. So, maybe this side we collect the responses and they are ultimately connected to this chain. So, this way we can have a very elegant way of testing the chips without taking them out of the board. So, if it is an automated process, that will send the patterns to the individual chips without taking them out of the board. So, that way the testing becomes easy. So, this is the concept of boundary scan, and with the invention of this core based design, so this testing process has become complex, and again the ideas of boundary scan has been incorporated into this core based testing mechanism. So, so these are the two things that we are going to see. So, apart from introduction, so we will see the standard 1149.1. So, this is an IEEE standard which is for digital boundary scan, where the chips that we have, they are all digital chips. Now, there are some advanced protocol 1149.6 which works for this analog chips also. So, if you have mixed signals chips, then this will work for that. So, we will not go into the details of 1149.6, knowing that it is otherwise similar to 49.1, but it can also handle the analog chips in its way. Then we will look into this embedded core test standard, which is 1500. So, this is an updated version of 1149. So, that can that is at a chip level. So, this 1149 is at board level and 1500 is at chip level. We will have a comparison between 1149 and 1500 also. So, the basic objective of boundary scan was to develop board level digital testing. So, at board level, so we do testing, but this is for digital ICs. Original objective was for digitalized ICs. Now it is also applied to MCM. MCM stands for multi-chip modules. So you have got a single chip, a number of chips found for that are mounted on the same board. So that is multi-chip module, and we have got field programmable gate arrays. So FPGA also the design is very much modular, because we have got the similar set of configurable logic blocks distributed throughout the chip. So if you want to test each of them, then we have to again send some test pattern to each of these CLBs, and that can be done using some chain architecture, so that the test patterns can be fed to these individual inputs of the CLBs. So that way we have got this FPGA also, they have got this boundary scan things. Analog circuit and high speed network, so they are, as I have already said, the 1149.6. so that is actually targeted to that. Okay, so it can use these analog circuits and high speed networks, and you can also go for verification, debugging, clock control, power management, chip reconfiguration. So for many various other purposes we can use this boundary scan. Basically it becomes a tool to command to various chips, like if a chip has got say different power modes, and if you want to change the mode power mode of a chip, okay, then you can send a command via this boundary scan, and then there may be an interpreter or analyzer available at the chip input, which will be looking into this command coming from the boundary scan, and accordingly it may reconfigure the chip to go into a low power mode. So that way we can have this thing. Similarly for verification and debugging, this is useful, because if we want to verify a design, we need to check what sort of values we are getting at different pins, inputs and outputs, and that can be obtained only by this. And debugging also, like something is going out, so is not working properly, so you can do a debugging there. So in mid 1980s there was an interface JE tag, and then in 1988, so that get modified to J tag. So then in 1990 it came up with the first boundary scan standard 1149.1. So there is a family. So this is the thing that I was talking about, 1149.1. So this is for digital chips and interconnect among chips. So standard is 1149.1 in 2001. So 49.2, 49.3 they got discontinued, because they are for digital extended digital serial interface and direct access testability interfaces, but they were discontinued. Then this mixed signal ICs, they came in a big way. As a result, this 1149.4, so this came for this mixed signal test buses. Then 1149.5, so this is for module test and maintenance, standard module test and maintenance. So this is this came up in 1995, but from 2003, so this is no more valid, and ultimately this one has come up 1149.6, which is now an accepted one, which actually combines many of these. Okay, so this high speed network interface, and it also it can also, apart from high speed, so it also takes care of this analog part. So the previously whatever it has been discontinued, so that can be taken care of by this one 1149.6. What is a core based design? So suppose it is like this. Suppose I want to design a system, so where we have got all these components, a CPU, DSP, some ADC, PLL, DAC, RAM, ROM. So okay, some more intellectual property designs, IP1 and IP2. Now if we want to design such a system, so forget about IP1, IP2. Suppose we take a very simple case, DSP, CPU and this memory chips. So they are there. Okay. Now if we want to design such a system, so what we have to do is that we have to take different components from different vendors and mount them on a PCB and do connection between them. So the disadvantage is that the CPU to memory communication, so that is going to be an off chip communication. So and we know that off chip communications are much slower compared to on chip communication. So this off chip communication being slow, one possible solution for this is to have this CPU and memory on the same chip, but that way one integrator, one system designer's requirement is different from another designer. So as a result, there cannot be any unified system that way. So what is required is that as a designer, I should be able to take different components from different vendors and integrate them into my chip. Now, when we do this thing, so I have to go to, say for example, Intel to get the Pentium design, I have to go to say TI for getting the DSP design. So, like that, but none of them can give me the design, because that is what they are doing. So, that is, so they cannot give it like that. So, what they give is nothing but a layout level description of the whole structure. So, and that layout level description, if manufactured properly, fabricated properly, that will give me the system. So, if I have that layout level descriptions of this say CPU, DSP, RAM, etc., and synthesize this whole thing together, okay, then all the off chip connections between say CPU and RAM, they become on chip connection. As a result, the speed of the system will be better, the performance, the system performance will be better. So, this is actually called the core based design. So, this layout level description that I was talking about, so they are called cores. So, these cores are taken from the vendors, and this they are actually integrated by the system integrator. So, apart from this say CPU, DSP, RAM, ROM, so you may need some extra logic which is not covered by any of them. So, some extra glue logic. So, this is commonly known as glue logic. So, that is just as if to connect all these components, this extra logic is necessary. There will be some interconnection between these components. So, that may be via bus, or that may be via some other interconnect mechanism. So, whatever it is, some bus and interconnect mechanism should be there. Some, if it is a system talking to the analog environment, then there must be some ADC and DAC components in it. So, that is also there. Then we have some special ASIC may be necessary, that may be known to the designer only. So, the ASICs are their descriptions are taken, and it may so happen that this IP, which stands for intellectual property. So, intellectual property core 1 and intellectual property core 2, they themselves may be another SOC. So, this, so they themselves may have more number of chips in them, more number of layouts in them, which will make that. Okay. So, as a designer, so I put all these things into my manufacturing process and get this whole thing done on a single chip. So, this is called a system on chip based design. Now, when we go for this system on chip based design, so there are associated test challenges. So, that we will see as we proceed through the course. To start with, we will look into the basic digital boundary scan policy 1149.1. So, we will look into the overall test structure, hardware components, instruction register, instruction set, description, scan description language, then the test support and the control architectures. So, this is basically the boundary cell, boundary scan structure. So, this is my internal logic. So, one chip may have this as the internal logic. So, if it supports boundary scan, then all its inputs, so they will be available on these scan cells, and all its outputs will also be available on scan cells. So, there will be two separate inputs apart from this functional inputs in the for this circuit, which is called the scan input and this scan output. So, all the internal lines in the sense that all the primary inputs and the scan inputs may be inside, there is a scan chain here. So, there is a scan chain here. So, that scan chain can also be accessible via these scan cells. Okay. So, that way this boundary scan chain will be made by having this boundary scan cells connected over a chain. So, this shows a board structure that has got 4 ICs. Okay. So, these are the 4 ICs that we have, and each IC is equipped with this boundary scan feature. Okay. So, all these inputs are connected over a scan chain like this. So, scan chain of these boundary scan cells. Now, it is connected like this. So, now output from this is again going to the next chips boundary scan input, again that way it goes. So, it traverses. So, this particular chain, it traverses the entire board. Okay. So, that way apparently it appears that it is very costly to reach individual chips, but still it is much better than going by the logic of the circuit, and most of the cases the logic of the circuit is not known, because we are buying the chip from the vendor. So, we do not know the internal logic. So, what should be the value given at a particular point at a chip level. So, that is so that I can get a signal propagated through the chip. So, it is very difficult to tell. In logic level, this was possible because the circuit description was known to us, the gate level description was known to us. So, we could use some sort of justification routine, but here I do not know the internal details of these individual chips. So, I cannot do any sort of logic justification there. Okay. So, the only way out is to have some additional chain made like this, so that all these inputs can be accessed. So, how does it look like? So, say this is the internal logic that we have. Now, there may be scan chains inside. So, these are the internal registers. So, all of them are accessible, okay, from this thing. Now, so these are the boundary scan cells, and this whole thing constitutes the boundary scan register. So, all these boundary scan cells put into a chain. So, that will constitute a boundary scan register. So, there is a serial test data input pin and there is a serial test data output pin. So, if this test data input is kept floating, then it is tied high. Similarly, there are some other points where it is tied high. Now, this test data input, so it can go to various places, like it can go to this chain of scan cells, okay. It can go to this instruction register, or there are some other registers, miscellaneous registers that we will see, and also there is a bypass register. Similarly, this test data output, it can get input from the internal registers, it can get input from this boundary scan chain, from this bypass register, from this miscellaneous registers, or from this instruction register, and there is a test access port control. So, controller, so which is not TAP controller, test access port controller. So, which will be giving commands to this test data output to select one of these inputs. Now, there is a test mode select signal. So, that will tell us that will tell the tap controller like what to do with the next input that is coming. So, whether it should go to the instruction register or some other miscellaneous register, or how this test data out will be controlled. So, all of them, so they are obtained from this test mode select line. So, that will tell the tap controller what to do. And then there is a test clock. So, that is the clock at which this whole testing process will operate, and there is an optional reset signal. So, this test reset signal, so that is optional. So, if you make this high, then the entire operation will be reset. So, we will see what is the meaning of this reset. So, essentially what we are having. So, apart from this internal logic that the chip will realize. So, it needs to realize all these extra components to make the chip this boundary scan compatible. Okay. So, if a chip follows this particular standard 1149.1, that means it has got all these components in it, and also its tap controller works in a particular way that we will see. So, based on the command, so it will work in a particular way. So, the hardware components of 1149.1, it consists of one test access port. So, this is the test access port that we have. So, test access port has got a number of signals. These 4 pins are mandatory: test data input, test data output, test mode signal, and test clock. So, these are the test data input, test data output, mode select, and this test clock. So, these are the 4 pins that must be there in any 1149.1 boundary scan. Then there is a test, then there is an optional pin which is test reset. Okay, that is optional. Now, one test access port controller TPAC, like in this case we have got this is the TPAC, the test access port controller, and this is the reset signal. Then there is an instruction register. So, there are certain types of instructions that you can give you can tell the test access port controller to do. So, this is actually that instruction register. It can hold different types of instructions, and we have got several data registers like this boundary scan register. So, this boundary scan register. So, these boundary scan cells. So, they will go in a chain, and that forms the boundary scan register. Then we have got a bypass register. So, this one is the bypass register, which can be used to send the test data input directly to test data output without affecting the chain that we have here. So, if certain information is not meant for this particular chip, it is for the next one or next to next one. So, all those intermediary chips, so their tap controller can be told that okay, it should configure the system in a bypass mode. So, then this tap controller will select this bypass register, and whatever is coming as in the TDI line will be sent to the TDO line. So, that way it can make the operation faster, the transfer of data through the chain faster. Then this there are some other registers like device ID register, design specified registers as scan registers, LFSRs for BIST, etc. So, basically the other miscellaneous registers that we are talking about. So, these actually include all these things. The instruction register is there, then the device ID register. Okay. So, then if we are trying to support BIST, so there may be some BIST register. So, all these are part of those special registers. Now, how this whole thing operates? First, the instruction is sent serially through the TDI to the instruction register. Okay. So, to the test data input line, it goes to the instruction register, and selected test circuitry configured to respond to the instruction. So, first this instruction is coming from this TDI and it is reaching this instruction register. So, this once it is there in the instruction register, so it will configure rest of the components to respond to the instruction. Okay. So, this is what is done. The selected test circuitry is configured to respond to the instruction. Test pattern shifted into the selected data register and applied to logic to be tested. So, if we see that the command is to shift in some test pattern through the boundary scan cells into the boundary scan register, then it can be doing some shift operation over a number of cycles. So, if the instruction is to start a BIST operation, then it will start a BIST operation. It may be to capture some response. So, that way it will be capturing the response. So, there are various instructions. So, this instruction register content is decoded, and based on that the other controls are set, so that this operation are done, and test response will be captured into some data register, and a captured response shifted out, new test pattern shifted in simultaneously. So, this is true for any scan chain configuration, that the previous response and the current pattern. So, they are shifted parallelly. Now, these steps number 3 and 5 are repeated until all test patterns have been applied. So, this is the way this whole thing works. So, what we need to do is somehow set this test data, the instruction register with proper values, so that it can be made to it can command the other components to work accordingly. So, this is the boundary scan circuitry of a chip. So, the how also it is a more detailed structure. So, you see what has happened is from this in the test access port, we have got this line, this TDI, TDO is the TDI test data input, TDO test data output, then this TMS test mode select and the test clock, and this is an optional reset signal TRST. Then that goes to the this tap controller, and also from the tap controller. So, it gives the clock. So, we have got these registers like this boundary scan register, device ID register, and design specific register. So, the bypass register. So, they are there. Now, there are some signals like clock to the data register, D register, shift to the D register, update data register. So, these are some signals. So, we will see this as we proceed. Okay. So, there are some cells, some registers in that we will see, and this instruction that is coming. So, that there is an instruction register decoder. So, it will be decoded accordingly, it will control all these data registers and this multiplexer. So, that the value will be shifted out to the next stage by means of either this from this multiplexer coming from this multiplexer, or it may be from the instruction register. So, this way this value is passed, and then so this is another register where this value may be directly coming from this TAPC, or it may be coming from this D flip flop. So, we will start with the boundary scan register. It consists of the boundary scan cells, then the bypass register. So, this is a 1 bit register used to pass test signal from a chip when it is not involved in the current test operation. So, this is basically bypassing the entire chain for a particular chip. Then there is a device ID register. So, for the loading of product information like manufacturer part number, version number, etc. So, there is a device ID register. So, later on we can say we can send some command to check whether this device ID matches with the device ID for which we are sending the pattern, and accordingly several such test patterns can be applied conditionally. And other the user specified data registers like scan chains, LFSR, BEAST, etc. So, they are also forming some data registers. So, this is the structure of a boundary scan cell. Okay. So, a single cell of the boundary scan register. So, you see that this has got two registers in it, R1 and R2. So, this R1 register, this is basically for storing the input pattern. So, whatever is so if you are trying to capture the response, then what we will have to do is that from okay, let us start with the normal mode of operation. So, normal mode of operation means that from the input the result should be available at output. So, it should not go into this boundary scan cells. So, in that case it is mode is equal to 0. So, this multiplexer will be selected. So, this mode 0 mode equal to 0. So, this is selected. So, this input goes to the output. Then the shift operation, that is whatever is coming on the test data input line, which is reaching here by this serial input line. So, that will be going to the serial input line. So, that will be going to this register R1. So, TDI, so that will go to in to out to TDO. So, that is the test data. So, basically it is coming from this shift data register. So, it will be coming from, if this bit is say 1, then the bit will be coming from this shift input. If the bit input is 0, then the input will be coming from this on the circuit functional input in. So, whatever is happening, so this value is getting transferred onto this one, say clock DR. So, shift DR equal to 1 and clock DR equal to 1. So, this will put this SI the serial input into this this register R1. Then in capture mode, shift DR is equal to 0 and clock DR equal to 1. So, shift DR equal to 0 means this line this input line whatever is coming. So, that will be put into this multiplexer and that will be coming to this registered R1. So, essentially in shift mode the test pattern is being shifted via this line, and in the capture mode whatever be the circuit output, so that is being captured via this input line. So, from in it is coming to this multiplexer to this R1. So, that is the shift and capture mode. So, one is mode 0, then mode 1 is shift mode, mode 2 is the capture mode. Then in the update mode, this content of this R1 will be available at the output. So, how this thing happens? So, this mode control is equal to 1 and this update DR is given. So, previously there was so update will be given after capture only. So, after capture this R1 is containing the value. So, that will be when this update DR is given, this value will be will come to this R2 as well. So, this value will be stored in R2 and then this mode is selecting 1. So, this is available at the output. So, this that way this R2 will be updated with the value of R1 and this will be output at this thing also. So, you see that in shift mode, so we are shifting in the test pattern and simultaneously the content of this D flip flop will be available at the scan out. The next input comes here, get last here, and the previous input goes to the scan out, through the scan out to the next cell in the sequence. In the capture mode, whatever is coming on the input, so it is getting captured onto this flip flop R1. Then after that, if there is an update operation, then this update operation will put the value into R2 and that will be available on the outline. So, this is actually the way these boundary scan cells operate.